All right, let's talk about your heart beating. So we got the autorhythmic cell. What's happening with the autorhythmic cell is we are doing beating this is the pacemaker of the heart. So these are like our SA nodes and our AV nodes, and they're actually causing signals to propagate through the heart. That way, the rest of your heart that actually has a ton of sarcomeres is pumping and beating and convulsing. So starting with our depolarization chart here, what's really cool about autorhythmic cells is they don't actually really have a resting membrane potential. They do sort of have a minimum they hit, but they never flatline like we're used to seeing with depolarization cycles. Instead, so starting at hyperpolarization, it climbs and climbs and climbs until it hits threshold, and then it depolarizes, comes down, climbs, hits threshold, and does it again. How does it do this? Let me tell you. So they have something called a funny channel. It's a funny name for a funny channel. Why is it a funny channel? Well, so in the past, sodium comes into the cell upon depolarization, but this is not the case for our funny channels. Somehow, somewhere, these channels decided that they're going to open at hyperpolarization. So if I refer to my chart, this is where Na plus IF. We abbreviate funny channels IF, or they're also HCN channels. HCN standing for hyperpolarization or cyclic nucleotides. Specifically, CAMP can open up this channel as well. When this channel opens, sodium, as you can see, is going to flow in. And we're going to get a bunch of positive charges, and that's going to gradually increase our potential of the cell until it hits threshold. Now, at threshold, what we're going to see is the belongs over here is going to come and hit this channel right here. This channel is a calcium type L and a type T channel. So first and foremost, the type T channel is going to activate because the type T stands for transient. Transient means fast. I didn't know that, but now I do. Calcium is going to flow in fast, and also through the slow, and L stands for slow channels. Flows in, and that's going to cause a bunch of other channels to open. More calcium channels are going to open, like right here, and we're also going to see, as more calcium channels open, then we're going to get signal propagation throughout our cell. We also have another pump called the NCX exchange, which is it's how we reset our calcium gradient. We're going to pump calcium out, we pump 1 calcium out for every 3 sodium that we pump in. This is utilizing the concentration gradient established by ATPase pumps, and it's using secondary active transport to bring the sodium, or to pump sodium or calcium out, and using the concentration gradient established so sodium can come in. That's what NCX does. So now that we've got these calcium ions have come in and they're propagating, we are going to come over to our cardiomyocytes, or also our contractile cells, because this is what actually does the contracting. So these guys do the pacemaking or the signal starting, and these guys are reliant upon the autorhythmic cells to actually make something happen. So you can see we already have a gate open because let's say we had a calcium ion or a sodium ion or whatever, something that's going to be causing depolarization to occur. This channel opens and this guy is going to enter our cell over here. When he enters, starting at 4, we're going to start climbing up. So phase 0, I'm just going to put positive charge enters, what we see right here. And then we're going to increase and increase. And this is where it looks a lot more like a typical cell, where as soon as we hit threshold, then a sodium channel is going to open and depolarize our cell. So we see sodium come in, that gate's going to open right there. And then this sodium channel, or the sodium ion, is going to cause another belong and start hitting, well, I guess I have a drone over here actually, causes another belong and causes our calcium channels to open. So referring back to our action potential up here, we see a 1 to a 2, and it's kind of like this weird fade, or weird plateau. We see a weird plateau up here. It's because we have a lot of stuff coming in and going out of the cell all at once. But the first thing that's going to happen is we're going to have calcium and, sorry, I accidentally had an extra one. So we only have calcium slow channels inside this cell, and calcium is going to come in, and it's actually going to come and open a channel on our SR called a rhyoiodine channel, and it's going to allow calcium inside the SR to flow out. So when the calcium flows out through our calcium L channel, this calcium is going to influence the opening of a bunch of these potassium channels down here. Now, they're in varying degrees of speed. Potassium, I kept saying calcium, I meant potassium. Potassium channels are going to be influenced by calcium. These are all in varying speeds, so as we go, let's say this way, they get slower. So this is a potassium transient channel, sort of like our calcium transient channel we used over there, super fast, opens fast, closes fast. Same with our ultra rapid, rapid, and slow, and that's going to allow potassium to leave the cell and help our cell to become more negative. Also at this point in time, up here, we have chloride channels opened by our calcium, or the calcium from here, and that allows chloride also to enter the cell up at the top. Eventually, our concentrations of all this stuff moving is going to be able to cause hyperpolarization again, or repolarization again, and our cell potential is going to drop. To help pump out this calcium that we brought in from right here, we have another NCX channel over here that pumps calcium out and brings sodium in, and then we also have our circuit pumps on our SR that's going to pull back in the intracellular calcium back into the SR. I think that's it. All right, and just an amendment to what we're talking about earlier, there is actually a way we can control heart rate using muscarinic receptors. If you remember, muscarinic receptors, they're associated with the parasympathetic nervous system, so they react to acetylcholine. So let's say we have some ACH released by our postganglionic neuron that comes and attaches to M2. M2 is going to have some sort of intermediate that comes and attacks GERK1 receptor. So GERK receptors, their whole point is to let potassium out, but they're going to do that through a kind of a funky method. So potassium 1 is going to have a gamma subunit, and when it's attacked by this, whatever's released from the muscarinic receptor, that gamma subunit is going to come attached to GERK2. GERK2 is then going to open and start acting like a potassium leak channel. So it's going to allow more potassium to leave. When we allow more potassium to leave, that's going to net influence our cell to become more negative. If I were to draw what that would look like on here, that would actually decrease the slope of our phase 4, which would then make our cell more difficult to depolarize, and that would therefore make our heart beat slower. Alright, and for the last part of this video, notice my outfit change, thank you. We're going to talk about ECGs and the process of that. So in an ECG, what we're measuring is we're measuring the charge on the outside of the cells. Typically, when we're thinking about depolarization, I don't know, for me I usually reference the inside, but we need to be thinking about depolarization and repolarization of cells from the outside perspective. So as the cell depolarizes, we normally say the inside of the cell becomes more positive, but the converse is actually true where the outside is becoming more negative, right? So this is a measure of how negative the cell is. We're going to go through each one of these individually. Starting with the P wave, this is what's called atrial depolarization, meaning our SA node up here has sent a shock wave out of depolarization stuff, and it's causing all this muscle, not the ventricles themselves of course, but all the muscle to depolarize. And that's what we see as a P wave. We see it like this because as we move our charge this way, we're moving a positive towards a positive, and that causes an upward inflection. On our Q charge, the first thing that we're seeing, notice how we go down, and the reason for that being is once the SA node hits the AV node in the interparticular space, what happens is our initial propagation is actually, so this is our AV node, that red dot right there. And if I were to draw, we're looking at the heart like this, but if I were to flip it downward, so let's say, my AV node would be right here on or next to the right atria. So when the SA node comes and activates it, before it starts propagating downward, it actually needs to propagate this way. It needs to fill the diameter or the circumference of the tube of the atrioventricular space before it starts going down. What that ends up looking like on here is we get a net movement this way. And so we're moving a positive away from positive or positive towards a negative, we could also say. And that results in a downward deflection. Once we fill up this space, we're going to fill the entire tube, which means we're going positive to positive, which causes a huge upward inflection. This is our largest part in ventricular depolarization. And then, this has also been done, as we're getting to right here, because the left ventricle is so much thicker than the right ventricle, it's sort of the last spot to depolarize, and that's why we see almost kind of like a hyperpolarization event, but really it's just when we're depolarizing, we're causing a net movement of charge that looks like it's going from positive, negative. So we're going positive towards a negative, which causes an upward inflection, or causes that downward inflection on the S. On this heart down here, when we repolarize, which is what the T wave is, ventricular repolarization, what happens is we are now moving a positive towards a negative, but in our ventricle, or in repolarization. So our rules flip a little bit. Here, if we went positive towards positive, then that resulted in an upward reflection. But if we go positive away from positive in repolarization, that results in a upwards inflection. So here, positive towards positive, upwards. Here, positive away from positive is also upward. See how we're flipping those two back and forth. And that's ultimately what causes our ECG wave.